Niranjan is a researcher in HP Labs in Palo Alto, just up the road. He's in the document automation lab there, working on work which basically supports his paper.
Thank you very much. So this talk will be about some of the work that we did at HP Labs on probabilistic modeling for automated document composition. One of my co-authors, Jose Bento, is here from Stanford University. He was an intern when part of this work was being done. So why automate document composition? And you saw pretty good reasons in the keynote address, but essentially, just to repeat that, you have lots of content publishers looking to target audiences, right? So they want personalized content that is very specific to their user preference. And also, you have to deliver this on a plethora of device formats. So the necessity to, you can't have a human in the loop kind of designing everything, although you'd be surprised how much manual design goes on in actually delivering to pads and so forth. So technically, what does this involve? Automated document composition, in a broad sense, requires the arrangement of multiple content blocks of varying size, number, and logical relationship onto multiple pages in an aesthetically pleasing manner. Now, I've shown on the left side here, a typical content structure. You have a bunch of text blocks, and they typically could be in XML. I've just shown it as a figure for example. And you have logical relationships, and you have some figures over here. And the logical relationships here refer to, if a text block refers to a particular figure, then in the layout you need them to be close together. Another type of logical grouping is a sidebar grouping, where specific text and figures that are in a sidebar need to appear together on the same page. And so the objective is then to arrange these in a nice manner, and to size the figures and everything, make it look good, aesthetically pleasing. But what is aesthetic pleasing? And that's kind of one of the issues why automation is hard. Just given the content structure, and each person gets his own content structure, you just get some text and figures, and to lay it out, you need to have an understanding of what looks good in the end, right? What's aesthetic? So there's no universal model for human aesthetics. I know there's a lot of work done, and a lot of this conference on these macro models of aesthetics, which try to model harmony and balance of a document and so forth. But it's still a hard problem. And even if documents could be scored on quality, there's an infinite or intractable number of possible documents to score. And as an example, I'm just going to, and also to introduce some notation that will be useful later on, I'm going to give an example. The content set C is the content to be composed. Now, in this case, it consists of 3 lines, L1, L2, L3, and a figure, F1, while the set of possible content allocations to one or more pages is a much larger set to begin with. For example, you could allocate the figure first to the first page. You could allocate 3 lines of text to 1 page. You could allocate 3 lines of text to 3 pages, and so forth. So for each of those allocations that are possible, you have multiple ways to arrange content on the page. You can put the figure on the top, figure on the side, off to the left, and so forth. And for each of these possibilities, there's an infinite way to manipulate image sizes. Image can be a little bit smaller, a little bit bigger. The white space can be a little bigger and smaller. What do we do? So essentially, you can see even for this case, technically, there's an infinite number of possible variations on layout. So if you look at the state of the art in automated document composition, I'm just going to refer you to the 2 fine review papers there to kind of go through the pros and cons of the various methods. But I will say that our method, unlike XML-based frameworks like XLFO and so forth, and further advances on that like DDF, it's a mathematical framework rather than an XML framework to do layout. And it tries to incorporate or try to unify a lot of the work that has been done on handling page edits, edits on a page, pagination problems, and template selection for layout into one framework, which we call the Probabilistic Document Model. Now, the first thing we need to understand is the Probabilistic Document Model is a representation of designer choice. So we try to model the choices that designer makes in creating a document. And we think that there are 3 fundamental choices a designer makes in designing a document. There may be more, but we model 3 fundamental choices. The first is pagination. What content should go on page 1, what should go on page 2, and so forth. We model that with this, with what we call a random set, C. And the less than equal to I says that for c less than or equal to 1, it's all the content up to and including the first page. C less than or equal to 2 means all the content up to and including the second page. And there are many possibilities for it. That's why it's a random set. You can pick, say, the set 1 that I've shown here. That's one possibility. You can pick something different. So you have random possibilities to choose from to make a content allocation to one or more pages. Then you have the content arrangement problem. So when a designer thinks about how to lay out content, he thinks, OK, how am I going to arrange this on the page? And in his head, he may have many possibilities of how to do this. But because we can't have these infinite possibilities, we try to model that with a template library. So if you have a large template library, essentially we model the choice of a relative arrangement to use as a selection from the template library. So each of these has an index. So when t takes the value 1, it means you selected the first template. T takes the value 3, you selected the third template, and so on. And finally, you have the notion of page edits. I mean, should I nudge this? Should I make this a little bit smaller, make the white space a little bit bigger, and so forth? So in this case, we can think of a template as being parameterized by theta, which is a bunch of thetas, which are basically parameters of the template. And they're basically all continuous. That's another compounding problem, because there could be infinite possibilities, right? Some of the specific things you can consider, for example, how much white space should be between elements and so forth. And this is also a random variable, because for every choice of parameters, you're going to have a different layout. For example, if I made this theta 1 and theta 2 smaller, the figure is going to get smaller. If I made theta 3 larger, then you're going to have more white space on the page and so forth. And these are some of the design choices that we try to model with these random variables. And the compounding factor is that they're not independent. You can't just deal with one of them, and because they're all coupled. You can't make a decision about arrangement without also having done something about the pagination and so forth. So the probabilistic document model is essentially a unified model of the design choices that explicitly couples together these design choices in an interesting way. So there's many ways to couple these design choices. When you're thinking about layout in your head, you have many ways you can, you're doing pagination all at the same time with relative arrangement selection and so forth. But we've chosen a specific way to couple these design choices together. These here arrows show the dependency between the design choices. And the reason we do this is mainly we told you why the automation problem was hard. One is the lack of a well-defined model for aesthetics is one, and the complexity of the problem. And so this formulation tries to get you a well-defined formulation for the aesthetics at a local level, which is much better than macro definitions of aesthetics, and also tries to have efficient algorithms that you can solve to get the layout computationally fast. Now, in this structure, you can see that each of the design choices here is associated with a probability. So, and those probabilities basically depend on the parents. So, for example, the design choice for the parameters, I'm pointing here, design choice for the parameters here depends on the prior design choice for the template that you use. So what does this mean? So let's start from the beginning. So you choose a template, right? So you have a design choice about the template, and you look at the probability distribution that kind of defines that choice, and you say if you tend to prefer certain templates for the first page, then those templates will be preferred. For the second page, a different set of templates may be preferred. So this just indicates preference of templates and so forth. The second one, theta, is basically parameters for the template. Now notice that it's not by itself, it's a conditional probability, so it's a local decision that you have to make based on, given a template, certain parameters are more preferred than other parameters. So this is where a designer, somebody who needs to know, a machine may not know which parameters are more preferred, right? So a designer would know, for example, given this template, this white space should be between 20 and 50 points, and it can vary widely. It's not a big deal, and so forth. So this preference, and notice that this preference is not dependent on content. So it's a prior preference before seeing the content. So it's like a prior probability of these parameters. Finally, given the template and the parameters of a template, if I fix the template and the parameters of a template, essentially I've given you a static holes in the template, right? And if I then also give you all the content that's been placed on the prior pages, then I'm basically giving you the design choice for a pagination problem. Basically, what I've done then is said, if I have some content to place on the current page, then how well does it fit into those slots? So I've turned that the pagination problem now into a local decision about how well content fits on the page. This probability also encodes references that you mismatch, because in the prior content that you see over here, I'm just trying to probably use this. So the prior content actually may have some references that are skipped from the current content. So the probability will be low or higher depending on whether you skip references or the logical structure is not met. So essentially, this is a micro model for aesthetics. Every design choice has its own aesthetic probability distribution, which you can say, did you make a good choice or a bad choice? And so you put it all together over I pages, and so you essentially get then an aesthetic model for the whole document that is composed of these micro choices. And this is different than a macro aesthetic model, which can designing and figuring out the harmony or symmetry or anything like that. Each of these decisions can be more or less well defined, and only the human actually really comes in only for this one because it's abstract. The machine cannot know. Machine can decide whether things fit, but human needs to decide which is more preferable. So using this model, we can actually generate documents. You can sample, you can take a template, you can sample parameters, and then you can fill content into that template, and then you can evaluate and see how well you did. And obviously, you try this many times, you're not going to have much luck. It's like a monkey throwing darts, right? You're going to end up with bad scores. But we can then ask ourselves the question, is there a sequence of design choices that you can make that will actually maximize this over all possible documents and all possible page counts? When I say a document is nothing but a sequence of design choices. A document composition is a sequence of choices for arrangements, choices for the parameters, and choices for content allocations on the page. So this is what we come to next. How can we efficiently solve this model in a very general, because right now I've not made anything specific. It's applicable to arbitrary document composition at this point, at least the model is. So our objective is to optimize this. So we go back here and do, from high school algebra, we say this function has variables. These are the variables of the function. We go one at a time and try to say, how can I optimize it with respect to theta? And then take out theta, and then optimize it with respect to t, and then optimize it with respect to the other one. So first thing I do is collect the terms that involve theta. So these two appear to involve theta, so I group them together and maximize over theta. Now, interesting thing pops out. This, as I told you, was like a fit term. It's how well content fits the page. And this is a prior on the preference for the parameters. So what this tells you is basically that in maximizing this for theta, if you have more than one way to fit the page, you're going to choose more aesthetic outcomes, because this will be the same, and then this will dominate. So you're going to choose more aesthetic outcomes. Another way to think about this is if you have a prior on aesthetics, and having seen the content, the prior becomes a posterior. Your belief about the aesthetics is changed, and this becomes a posterior probability. This is a map problem, maximum posteriori estimation problem, which also makes sense. So once you have this in any case, you've eliminated theta, and so you have these other three variables. And you go back to your previous thing, and you say, OK, now I take the other variable that's left over, combine it with what I just had, and do an optimization to remove t. So here I optimize over the templates, and I get this other function that does not include the templates. And then I go through for each of the content allocations, and I do the same thing, and essentially end up with a recursion. Now, what you can see are these. You can think of these as fundamental equations coupling those design choices that you had, and you can see the design choice for the pagination depends on the arrangement, which in turn depends on the page edits, and so they're all coupled together in a nice way. So anyway, when you continue this, finally, at some point you'll hit when you've exhausted the whole content, and C less than equal to I will be the full content C, which you started with. And then you go and look and say, of all these possibilities, which choice of page count will give me the highest value? And you pick that for the document count. I mean, how many pages the document should be laid out in, right? And once you do that, you have this and the content, and you can back substitute. You can go back here and say, now I know which page count it is. I know this value. It's this final value. And now this is only one variable problem, and I can solve for that variable. So that's a backward pass, basically. And you can, when you read the paper, you can actually go through it in more detail and figure out if it's not immediately obvious. But you basically land up with an optimizing value for the content allocation. You can go and substitute that. Now you know these two. You can substitute in the previous equation and get the template and keep going. The nice thing about it is that we just did basic algebra. We didn't do any suboptimal thing. I didn't make any approximations or anything like that. So solution is globally optimal with respect to our aesthetic model and is equivalent to fully exploring the infinite design space, including the continuous parameters and everything, provided that you solved, you're able to do this maximization. So what's the fundamental? Okay, that's nice. You got an algorithm. It's able to evaluate thing, but how complex is it? That's the key question, right? So here, basically, I've just replaced those C's because, for notational convenience, this B denotes the previous content, and A denotes all the content, including the previous content. And this shows that map optimization problem. Now, A's and B's come from a set of possible allocations, as I kind of introduced you to that earlier, that is C prime. And so, if you can take all possible values for A and B, this will be order C prime squared. It will be quadratic in C prime. And if I look at this one, because I have page count coming in here, which page count is proportional to the content itself, because the more content you have, the more number of pages. This is going to be this one, and this essentially dominates the computational complexity of the problem. But you can do better than that, because if we bound the content on a page, then basically what we're saying is, on a particular page, we want no more than 4 figures and 300 lines of text, right? I mean, if you know your page, you can say, well, that's reasonable. If that's the case, then this B does not grow, because B is tied to A. It's just always close to A. It doesn't grow with the content. And so this complexity, you can lose the square there, and so it becomes that. Also, C prime is basically dominated by the content squared, as you can see over here, as the content gets large. So this is basically a cubic complexity in content. So your document composition in this case is cubic in content, but we can do better. Right now, we've assumed that for each page you have a different preference over templates. So certain templates for page 1 are more preferred, but if you were to say there's no such preference, then the dependence on I goes away, and you can do a neat trick. What you can do is, when you're maximizing the tau quantity, the previous equation, you can just move it inside. There's no term I here, so you can move it all the way in, and you get a recursion that is independent of I. And hence, the term that depends on I, the C, goes away, and now you have a quadratic complexity. Finally, this quadratic is because, essentially it was C prime, it was just C prime, and we substituted C prime, C squared for C prime. Now, there are certain cases when C prime is equal to C plus 1, actually. It's pretty close to C. That's the case when you allocate content in the order in which it is there. So you don't actually allow figures to float too much. In other words, if you basically you allocate content in the order that it was received. So if you had a figure, then it either has to appear on the same page or the next page as the prior content that was just before it. And if you're willing to make that choice, then you essentially get a linear complexity. Now it becomes linear in content. So without making any specific assumption other than by just coupling these design choices, we've come up with a model and also a solution for that model that gives the optimal aesthetic score in linear complexity with the content, which is nice. Now the question is, how do you actually parameterize? If you actually use the model, you need to actually put in some values for the probabilities, right? Otherwise it's just theory. So in this case, what we do is, we have a very simple model for now, and later we're exploring ways that we can learn the model, because once you have a probabilistic model, one of the nice things, you can start learning it from data, right? But for this work right now, what we do is have a designer set this. Now, remember, theta given t is a preference. It's preference for certain parameters over others. Now, I'll take a very simple example of a white space. Right? It's between 20 and 60 points. And if I give a mean and variance, typically designer gives a mean, variance, min, and max. So if I give it a tight variance, then basically it's saying that you should not, you want this value to be enforced very carefully. If I give it a loose variance, then it can be changed. You're basically, designer specifying his intent that that parameter can actually move freely, right? And if you have multiple parameters, the algorithm will automatically trade off and figure out which parameters it can move more freely and which parameters it doesn't move more freely and so forth, because they're encoded in the aesthetics. Now, this means there will only be a diagonal. It's kind of wasting this multivariate model, because now it's only getting a diagonal if you just do every parameter independently. You can also encode linear relationships among the content. Anything of the form c theta equal to d, you can put a precision on it, and you can get some off-diag. You can basically write a closed form solution that gets some off-diagonal terms. And this is especially useful when you're dealing with aspect ratio. So let's say you want the image to be close to its original aspect ratio, but you want to allow the aspect ratio to change. This is nice because you have a lot of image retargeting algorithms today, which are not being used that much in layout. It would be nice to use them. So you say theta w by theta h is approximately a with precision rho. And if the precision is very high, then you say, don't mess with my scaling, right? Just let it scale. But if the precision is loose, then you allow the reformatting algorithm to do some reformatting on it. And we also need to define fit. So basically, to define the fitting score, we calculate paths to the document. And this is just one instance. I'm sure we can come up with other parameterizations and so forth. And based on this, we can just turn this graph into matrices and basically make the computation fitting along each path. So along each path, you're looking and seeing how well is the width of the page. Is the width of the page being filled by these parameters or not, right? And is the height of the page being filled or not? And then here you have the term which I was talking about, which is the logical structure of the document, which says, are you missing any references? And you can penalize the missed references. The nice thing about it is if you put these two normal distributions together, the product is also normal. And you can technically write down the solution in closed form, except you have some lower and upper bounds. And so it becomes actually a constrained least squares optimization problem. Otherwise, the answer just would have been A inverse B, right? So once you solve the innermost problem, it's efficient to solve. You notice that the innermost problem does not grow with content. We're in business. And then you can actually, it shows an operational view of what you're actually doing. The designer encodes these templates and styles. The content comes in and without any knowledge of style. And then you're able to churn out the layouts. Here's an example input. I haven't spoken about it, but we can support alternate versions. Optional images can be supported. You can say I want the output in 2 to 4 pages, or 1 page, 2 pages, so forth. Here's a basic template editor showing the different relative arrangements you can generate. You can pull it in, and you can set the precisions and the means and so forth on different things. And you can play with it a little bit more. The style sheet for the fonts and everything. And you can also put some banners and other decorative things and apply them to templates. It's a very simple basic editor. So you have some content here. More content, it reformats. Yet more content, multiple pages pops out, different content. And here we just want to compare with hard encodings. Hard encodings of aesthetics basically says that it's basically evaluating fit, because what it's doing is one-way constraints say you shall start this document, 10 points below this or 10 points above that, and it's only evaluating fit. So in this case, we can be more flexible because here the image is allowed to move to fit the content because the prior was defined loose. It's a low prior. If you had a higher prior on the image, then the white space moves up and is able to accommodate the content. And in this case, no matter what you set the prior as, because the prior is only a prior, the likelihood function dominates the prior. In this case, you want to fit the content on the page, and so it just ignores the prior. So that's nice to be able to, if you want to enforce, the prior only kind of informs you if necessary. So this is multiple document format. The same document, because I've tied each parameter to the height and width of the page, so it's automatically adjusting to reflow the content and reformat it, making those design choices appropriate for that form factor or whatever, and laying it out. So we also did the HP Labs 2010 annual report, and that's downloadable. Here, we were not allowed aspect ratio changes. So basically, and the main consideration was to have images appear close to where they're actually being referenced. And you can see a design choice here where it actually made the image slightly smaller, scaled it up so it matches with HP Lab Singapore. And where it could have put it on the other page, but it made this choice to make it optimal. And it had sidebars and some extra stuff. So in conclusion, we have a general model for automated document composition. The specialization is not general, by the way. The specialization refers to a specific class of documents and the specific probability distribution that I had. But you can, hope in future people will come up with better parameterizations for this type of thing. We naturally incorporate soft probabilistic constraints and can be used to synthesize layouts if we got an efficient way to synthesize layouts. We've also, and I know this is Google talk, so we also have a nice MapReduce implementation. It's very conducive to MapReduce on large-scale clusters. And model distributions can be learned from examples, which that'll probably be presented next time. we're looking at more sophisticated models like multivariate mixture of Gaussians, which you can learn with EM algorithm and so forth. And right now, my sticking point is basically how do you model non-linear complex text flows around images in a way that's easily parameterizable and so forth. Thank you.